Yeah, I'm Charly Moras. I'm a research associate at the University of Hamburg, and I've been working a lot on understanding the dissolution of different minerals for ocean alkalinity enhancement. And the group led by Prof. Hartmann has been part of alkaline since the early days, and we've been trying to understand the different processes and how we can implement such strategy. So today I will be mostly talking about those dissolution kinetics and the consideration that we have to have for OAE application. I will be focusing mostly on the mineral additions, and I will be presenting different work, most of the work that our group has been doing, where we're trying to now have a great overview of everything we know and the last pitfall that are remaining. So we're talking about OAE right now as in terms of alkaline mineral addition. So it sounds very straightforward. It's essentially spreading alkaline minerals to lead to alkalinity enhancement. But realistically, there's a lot of parts that are still variable. So we talk about mineral types. Different minerals and different form of minerals will have different effects. The location or the seasonality will also affect those dissolution kinetics. And all of that falls then within what Abby was describing as the efficiency. So if we take that figure from Abby's work and we just focus on this first box, we have what she introduced as that incomplete mineral dissolution, and there are two big parts. So we do have this concept of dissolution. Does the feedstock dissolve as expected? Which factor can affect such dissolution? And also what happened to the lost fraction? And there is the second part, which is this particle sinking. And the main question is, are the undissolved particles sinking faster than they are dissolving? To what extent does it affect the carbon dioxide removal potential of the strategy? And also, like, is that alkalinity loss permanent or only temporary? So I will be focusing, like I mentioned, only on open ocean application. So that means that we'll not talk about liquid application because there is no dissolution kinetic, no sinking per se. I will only talk about minerals that dissolve fast enough, so calcium carbonates that don't dissolve naturally in seawater will be disregarded. And I will not talk about reactor technologies. We have 3 posters from our group, so you can come and see, and we will be addressing different points. But for today, I will talk mostly about mineral dissolution kinetics. So what is dissolution kinetic? It's a fancy word to essentially say how quickly and efficiently a mineral breaks down into a dissolved form. That means that we have a concentration variable, so we look at how much and how fast. And so essentially we're interested in how many grams, for example, per liter, per minute or hour are generated, or at least broken down. And to do that, we basically run experiments where we track the pH or the alkalinity changes. So this is an example of what a dissolution kinetic could look like. This is the work from one of our PhD students that has dissolved calcium hydroxide in seawater at varying temperatures and varying salinities for a target alkalinity of plus 500. That was the general idea. And essentially the pattern of the curve will be indicative of that dissolution kinetic. So you can clearly see that at 4 degrees, the top left, we have some sort of slower trend to reach this maximum value, while at higher temperature, we have a much steeper curve. So the dissolution kinetic per se is faster at higher temperature. There is more energy in the system. It's always more efficient at higher temperature. But it's also important to note that, in that case, the higher the temperature, the lower the maximum alkalinity generated. And that's one of those lost pathways that we're interested in. So we know that there is a temperature effect. We also know that the type of mineral has an effect. And when I mean type, I talk about grain size. So this is a figure from a research for olivine-rich mineral dissolution. And we can clearly see that the moment we have a smaller grain size, so that's the very steep line on the far left, the time required to reach the maximum is much faster than when we have a larger grain size. This is also true with magnesium hydroxide, where the smaller the grain size, the starker or at least steeper the increase in pH and the faster I get to my maximum. And this is basically due to what we call surface area. There is more particles for the same amount, so that leads to a faster kinetic. So we know that the grain size also affects that dissolution kinetic. A last thing that we have to take into account is the salinity. So the salinity is essentially a proxy to understand what is happening in your seawater that will give you some idea of how much dissolved elements are in there. So the more saline, the more elements in there, the less saline, the more room for things to dissolve. And what we clearly see is that, again, this is the work from Matthias, where we have dissolution of calcium hydroxide and magnesium hydroxide. You can see that the blue line leads to a higher efficiency. We have a higher ending point than at higher salinity, because the lower salinity has more room for calcium and magnesium to break down into. So we know that if we target fresher water, we might be faster at breaking down those particles. And this is about the dissolution kinetic per se. There is this thinking also component which is of interest when we talk about open ocean applicability, because the question is, like I mentioned, is the particle dissolving before being lost? We want the alkalinity to remain in contact with the atmosphere, so within this mixed layer, so we have to kind of account for this potential loss. So this is a work from one of our students as well, Stefan Baltruchat, who, with a very simple shrinking core model, could simulate how fast it would take for certain mineral of interest. On the left, you have calcium hydroxide. On the far right, you have brucite, before being lost to the deep sea. And what we can clearly see is that calcium hydroxide is easier dissolving and dissolves faster before it sinks, while it seems that magnesium hydroxide could take longer and be lost below that mixed layer depth. It is important also to take into account that in colder water, this mixed layer depth is deeper, so we have a bit more room to play with. But in general, magnesium hydroxide will sink faster than it dissolves. And this is true if, with those data, we start inputting the dissolution kinetics that exists from literature. This is the kind of idea you can get where you see where and what fraction of the minerals dissolve in the water column. So you see, again, calcium hydroxide on the far left will dissolve within the first meter. Magnesium hydroxide would be dissolving at about 30 or 50% before reaching this mixed layer depth. So this is the kind of thing we're trying to understand and take into account when we report on the efficiency of OAE application. And so essentially, calcium hydroxide will perform better for in open ocean or in the surface ocean than magnesium hydroxide. So now, what is the idea with all of that? The idea would be to try to have some sort of matrix that we can use to report on the efficiency for a given salinity, temperature, and grain size. And so what we've done is inputting those values following, again, like the work that we've been doing, into these kind of isoline, very fancy-looking graphs. But essentially, that tell you that for which salinity and temperature you have an efficient dissolution. Again, the target is 500, which is what you have at the bottom left on the left graphs. And you can see that the higher the temperature, the more loss of alkalinity I have. This is also true for magnesium hydroxide, where it seems that salinity past a certain level would have some sort of effect. And using those data, what we can do is that we can put them into an ideal scenario of where would be the interesting conditions to have a high efficiency. So this is purely lab-based. This is not a model. It's just inputting the data that we've measured in laboratory experiments and see which areas would have a more suitable condition to have a more efficient dissolution. And so what we can clearly see is that the colder and fresher water seems to generate a nearly 100% of alkalinity release compared to the warmer temperatures. This is a spoiler, but I won't get into details. I think Matt will talk about it more. This is most likely due to lack of dissolution and precipitation of calcium carbonate. If we remember, the colder water, the slower the kinetic, which means that the slower or the harder it would be to precipitate something, which is why the colder water seem to behave better, or at least have more potential. And so the idea with that is trying to connect all of that to now general global models, where we could put into these models the dissolution kinetic, the sinking, that will take then into account vertical and horizontal mixing to have an overview of the general potential of OE for given materials around the globe. And a side note, based on work that has been done by actually people that are in the room here, Kai, Lennart, and Andrew Dixon, may not be here, we can, from a carbonate chemistry perspective, have an idea of how efficient the CO2 capture would be for a given alkalinity. And it turns out that we have some sort of correlation with the two, which is encouraging, though it needs to be, again, put into model. This is purely lab data, but it would be encouraging to see that the fresh and colder water may be more efficient at generating alkalinity and potentially more efficient at capturing CO2 due to the carbon system. Due to the carbon system. That would be it for me. Thank you very much.